Okay, this question is shown below, 0.3 times 0.4 meter square plate slide down along 30-degree incline on which there is a film of oil 0.5 millimeter thick with viscosity mu equals 0.1 kilogram per meter second. Assuming that the plate does not deform, the oil film. Estimate the terminal sliding velocity, the time required for the plate to accelerate from rest to 99% of the terminal velocity. So I think you already know about the terminal velocity. So it is actually the constant velocity that occur on that object. So for example, the idea is very simple. If you are a parachuter, so you jump from your aeroplane, so you will go down, but suddenly you will find that the velocity is actually constant. It's not keep increasing. Okay, it's quite weird because sometimes we could say that gravity is acceleration. So acceleration means your velocity is keep increasing because the equation for acceleration is v2 minus v1 over times. So means that there must be a larger v2 velocity compared to the v1 divided by time. That's create acceleration. But however, in real situation, we found that because our mass is constant, so actually gravity cannot pull us faster and faster. So means that we will dropping, we will falling at constant speed. So that constant speed is called the terminal velocity. You can check about that. Okay, same with this situation. We found that if we have this situation, we have an oil here and we have an incline of 30-degree here. So we have a box here, and then because of gravity pull this one, so it will sliding down like this at certain time, so the velocity will remain constant. So the question is, what is the terminal velocity, and also the time required for the plate to accelerate from rest to 99% of the terminal velocity. Okay, so this is the idea of terminal velocity. So I think you could draw the free body diagram of that one. So we have a gravity pull like that, and then we could expand the gravity pull into x and y direction. So because this box is sliding at this x direction, so we take this one. So and then again, if we have an oil inside, an oil between these box, so we found that so oil will create resistance. So means that the force here, okay, at least must be equal to the resistance that act on the reverse direction, on the other direction. So the idea of this one is, as I said last time, so we have a shear stress here, tau, and then we multiple with the whole area of the liquid, of the oil. So we have a tau A here. So that's why we could write this equation, W weight sine theta, to get only the x component. So it is equal to tau A. So and then tau here, as I said when we derive the Navier-Stokes equation, so tau is equal to mu du dy. So and then we substitute with du dy here. So and then so we replace the du into a v star like this to reflect the terminal velocity. Okay, because there are no differential difference of u anymore. Okay, so we just assume it is just a constant velocity, so it becomes v star, and dy here will become the oil thickness. And then if we calculate, it is around 0.245 meter per second. So this is the idea how to calculate the terminal sliding velocity. So and then the time required for the plate to accelerate from rest to 99% of the terminal velocity. Why in this question we always use the idea of 99%? Because if we take 100%, there are no acceleration. So means that there are no difference between V2 and V1. So there are no acceleration. So that's why we always take 99% of the terminal velocity. So and then the word accelerate here maybe will give us some ideas, because if we see previous equation here, okay, we found that we have w sine theta mu du dy a. So du dy means the difference of u over dy mean over distance. So if we only have one u, so means we cannot calculate the acceleration. So that's why we need to be a little bit creative. So we found that, okay, actually the free body diagram will work like this. So the idea of this one is actually described in my previous lecture when we talk about the continuity equation. I say that input mass flow rate at inlet minus mass flow rate at outlet, so we'll have dmdt, mean something that remains in the system. Okay, something like this. So we have a box here, so we have the pull power here, the gravity pull the object here. So at the same time the resistance will resist like this. So however, for sure the resistance here is smaller compared to the force here. That's why the box can moving downward. So the distance here, okay, the difference of this force will give us acceleration. That's why we equal it with ma. You know, F is equal to ma, the common Newton's equation. So we have the ma here. Then we could say that we have one parameter which could show the acceleration. Now you have acceleration in your equation, so you should happy with this. So and then we simplify everything. So we know that sine 30 is 0.5, and then we substitute with tau du dy here, a, and then m is w over g. So mass and weight is totally two different things. So w here is mass time gravity. So because we want to take the weight here, so we change the m here as, okay, m is equal to w over g. So we substitute with w over g. So and then, okay, so here there is a trick. There are acceleration, but the question asks to calculate the time. So you need to create t parameter, time parameter. So how to create that? So we change the word a here into dv over dt. So dv over dt could express the acceleration. So that's what we do right now. And then we simplified everything, so we could get this one. And finally, we could have this term. So we have dv dt plus mu ag over wyv equals 0.5 g. So this is very special. So we need to solve it using first order linear ordinary differential equation. So in the next slide, I think you could understand how to solve this one. Okay, so we use the idea of integration factor. So let's say that integration factor is equal to e to the power of integration of p dot dx. So let's say we have this equation, and then we simplify that this is the p. Okay, so and then this is all the terms. Okay, so let's say it is equal to q. It is okay. So and then according to this equation, we could found that e integration of p dx. So we have the e is equation to integration of mu ag over wy dt. Okay, so this is dx, so but we have a dt here. So and then because we have a dt here, so and then it is equal to e to the power of so we integrate we integrate this one, so we could get it is e by the power of mu a g t wy. So and then we multiply our equation here with the integration factor here. So we put the e here, another e here, and another e here. So and then we do this one according to this basic rule. So we have d dx ex squared times y, it is actually equal to ex squared dxy plus dx e x squared y, and then is equal to this one. And then the equation 1 here could be written as this one. Okay, maybe this is very, I just go quickly here, but I think if you sit down and look back into this equation, I think you could understand how this, equation number 1 can be transferred to these terms. So and then after you get that, you could integrate both sides. So and then finally you will get this one, and then you have the value of c. So again, please do not simply say that c is equal to 0 unless you could prove it. So and then we divide into this term. So and then we could get this one, and then you could see that the constant is still there. So and then c is constant, we need to determine it. So we give them conditions. So normally we will go for the starting condition, which is at the top, at the beginning of the process. Okay, here, so at t equal to 0, so for sure the velocity is equal to 0. So if we substitute everything, so we could find that the value of this equation, okay, so the v is 0, so and then the t is 0, so and then we cannot simply put y is 0, because again, I already mentioned it last time, you need to understand each parameter in your equation. So the y here is the film thickness, so means that in this situation we could not assume that the film thickness here is equal to 0, so we remain the value of y as integer. So and then we could get this one, so and then we could rearrange. So we found that c is equal to negative 0.5 wy over mu a. So we substitute in the equation, then we could get this one. Okay, so and then from the previous calculation in part A, so it is simply we could calculate the value of terminal velocity as this one. So and then we rearrange because we want to calculate the terminal velocity. So we write terminal velocity is equal to wy 0.5, the value of sine here, over mu and a. So and then we substitute here. So and then we could say, we could replace this term into the v star. So again, the idea is very simple, because you didn't found any terms in your previous equation, means equation until this step, to show the terminal velocity parameter. Okay. So after this, so and then we put another condition, which is the velocity is actually the terminal velocity. So means the velocity is 99%, 0.99 before it becomes 100% terminal velocity. So we could write like this. So and then the t is equal to t star, just to reflect or just to show that the time is actually the time where the terminal velocity occur. So we substitute everything, and then we could do the mathematical solution here, and then from this equation, okay, we could find that the time to terminal velocity occur 99%, 0.99 before the 99% before the velocity terminal occur is around 0.23025 second.